Hello everyone, welcome back to my channel. So in this video we are going to learn about parallel comparator type ADC or flash type ADC. Okay, so flash type ADC. This is a simple circuit diagram. This is a simple circuit diagram of 2-bit flash ADC. Okay, so 2-bit flash ADC. So once you understand 2-bit, we can go for 3-bit flash ADC. Okay, so I'll explain you first a 2-bit flash ADC. If you understand the concept here very well, then we can extend it to 3-bit flash ADC also. Okay, because 3-bit flash ADC is somewhat complex. So first, if you understand clearly the concept here, then you can extend it easily to 3-bit ADC also. Okay, so here in this flash type ADC we are going to use priority encoder. Okay, so priority encoder with D3 as the highest priority and D1 is the lowest priority input. Okay, so this is about priority encoder, and we are using 3 comparators. 3 comparators are going to be used here, 1, 2 and 3. Okay, so for each and every comparator, the non-inverting terminal, that is the plus input of each comparator, is applied to the analog input voltage, which we want to convert it into digital. Okay, so analog voltage which we want to convert into digital is applied at positive terminal, that is non-inverting terminal of each and every comparator here. So here we are applying, here we are applying, and here also we are applying the same VA. Okay, so different resistor voltage, different resistors are taken and voltage drops at different values are going to be taken across inverting terminals at each and every comparator. Okay, so here the voltage is different, and here the voltage is different, and here the voltage is different. So we'll find that voltages, don't worry. Okay, so different voltages are going to be applied for different comparators, so that your output of comparator may be either 0 or 1 depending on the 2 inputs. Okay, so depending on that the outputs of comparators, the priority encoder will make the corresponding digital output. Okay, so this is how analog input voltage is converted into digital output. Okay, so we'll see one by one the operation of 2-bit flash ADC. Right, so the voltage here, first the voltage we have to find. So the unknown voltage, which I am taking it as Vx here, Vx is equal to the voltage, supply voltage is VR into, so we are finding the voltage across this resistor, right? So voltage across this resistor, so voltage across this resistor is R divided by total resistance is 4R. So R gets cancelled, so it will be VR by 4. So the voltage here is VR divided by 4. And if you want to calculate the voltage here at this point, okay, so at this point if you want to calculate the voltage, what will happen? So at this point voltage will be, so the resistance will be 2R, right? So R plus R. At this point the voltage will be 2R. So the unknown voltage is VR into 2R divided by 4R. So it will be 2VR by 4. So RR gets cancelled, so it will be 2VR by 4. So the voltage here will be 2VR divided by 4. Similarly, the voltage here will be 3VR divided by 4. Okay, so this is how we can find the unknown voltages, and we know the operation of priority encoder also. So if the highest priority D3 is equal to 1 irrespective of D2 and D1, so we don't care about D2 and D1. D2 may be 0 or 1 and D1 may be 0 or 1. Okay, so it may be either 0 or 1. If we don't care about that, so when D3 is equal to 1, what will happen? Okay, so D3 is equal to 1, then output will be 1 1. When D3 is equal to 0, the highest priority input is 0, and then the next highest priority D2 is equal to 1. In this case the output will be 1 0. Okay, so when D3 and D2 both are zeros, the first highest priorities are zeros and D1 is equal to 1, then the output will be 0, 1. Okay, so here D0 will also be there. D0 is connected to ground. Okay, so in the priority encoder, D0 will also be there, so D0 is always connected to ground, so we don't care about the D0. Okay, so this is the operation of priority encoder. So if the highest priority is 1, if the highest priority is 1, then its corresponding output will be obtained across the priority encoder, irrespective of D2 and D1. Okay, so if D3 is equal to 0 and D2 is equal to 1, so now the highest priority is D2, because the highest priority input is 0. So next highest priority is D2, which is equal to 1, then its corresponding output is going to be obtained, which is 2. So this is 3 and this is 2. Similarly, the first two highest priorities are 0 and the next priority is 1, so the corresponding output will be obtained, which is 1. Okay, so this is the operation of priority encoder, which we already have discussed, right? So we'll discuss about this later in digital circuits. Okay. Okay, so this is how we can find the voltages, and this is the priority encoder concept. So based on this, now we will form a table for different values of, because we have different ranges of Vin. So for different ranges of Vin, we'll form a table. So for Vin range, here we'll write a D3, D2, D1, D0 and AB here. Okay, so 0 less than Vin less than or equal to VR by 4. VR by 4 less than Vin less than or equal to 2 VR by 4. 2 VR by 4 less than or equal to Vin less than or equal to 3 VR by 4. 3 VR by 4 less than or equal to Vin less than or equal to VR. Right, so for the first case, 0 less than or equal to Vin less than or equal to VR by 4. So what will be the output of these comparators? So for the first comparator, if you see for the first comparator, and this is second comparator and this is third comparator, I am drawing for the 3 comparators. So plus minus plus minus plus minus. So here it is Vin. For all the comparators, the positive terminal is connected to Vin. Okay, so this is first comparator, this is second comparator and third comparator. For the first comparator, the negative terminal is connected to the voltage, which is equal to 4R by 4. So this will be 4R by 4. For the second comparator, the negative terminal is connected to 2VR by 4. So here the voltage will be 2VR by 4. For the third comparator, it is connected to 3VR by 4. So here it will be 3VR by 4. Okay. Right. So this is same for each and every range of these 4 ranges of the values. Now see here, in the first range, what is the maximum value? Maximum value is VR by 4 only. So when maximum value is VR by 4, so here I am taking the maximum value when Vin is equal to VR by 4, that is maximum value. So both inputs are same, yes or no? So both inputs of first comparator are same. So when both inputs are same, as I have told you, when I am dealing with a comparator, so output is going to be 0, yes or no? So here when Vin, the highest value is VR by 4. When the highest when it is VR by 4, then what will happen? So voltage at positive terminal, so V plus is less than V minus. So when V plus is less than or V minus, then the output is also 0. So voltage at positive terminal greater than voltage at negative terminal, then the output of comparator is 1. Voltage at positive terminal is less than or equal to, in both cases, the output is going to be 0. So this is the operation of comparator. So here the output at positive, the input to positive terminal is only VR by 4, but the input to negative terminal is 2 VR by 4, which means V plus is less than V minus. So in this case the output is going to be 0, output of comparator is going to be 0. So in this case also the output is going to be 0 because the voltage here at positive terminal is VR by 4 and voltage at negative terminal is 3 VR by 4. So V plus is less than V minus. So in this case also it is going to be 0. So output of each and every comparator is going to be 0. That means that 0 is applied to D3. So D3 is going to be 0, D2 is going to be 0, and D1 is going to be 0, and obviously D0 is also 0. When all the inputs are 0, then priority encoder input is also, priority encoder output is also 0. Okay. Now see the second case. So the highest value here present is 2 VR by 4. So V in the value is 2 VR by 4. So here 2 VR by 4 and here also 2 VR by 4. So 2 VR by 4 and VR by 4 here. So in the first case, in the first comparator, V plus is greater than V minus, yes or no? So V plus is 2 VR by 4 and V minus is VR by 4. So V plus is greater than V minus, so this condition is satisfied. So output of the comparator is going to be 1. So output is now 1. And here 2 VR by 4 only. So here also 2 VR by 4. So V plus is equal to V minus. Therefore the output is still 0. And here 2 VR by 4 and here 3 VR by 4. So V plus is less than V minus. So in this case also the output is going to be 0. Because of this condition, second condition. So output of comparator is 0. So only the output of first comparator is going to be 1. So output of first comparator is given to D1. So D1 is going to be 1. This is anyhow 0 and the remaining all values are 0. So when D1 is equal to 1, as I have told you for comparator, when D1 is equal to 1, what will be the output here? So it will be 0, 1. So output will be 0, 1. Right. So for this range, now for this range, 2 VR by 4 less than V in less than 3 VR by 4. So now the maximum value is 3 VR by 4. This is 3 VR by 4 and this is 3 VR by 4. So output of first comparator is going to be 1 because V plus is greater than V minus. Output of second comparator is also going to be 1 because V plus is greater than V minus. Here V plus is 3 VR by 4. V plus is 3 VR by 4 and V minus here is 2 VR by 4. So V plus is greater than V minus, so it is output of comparator is going to be 1. So output of first comparator 1, output of second comparator 1, and output of third comparator is still 0 because V plus is equal to V minus. Because here 3 VR by 4 and here also 3 VR by 4, and still the output of third comparator is 0. Understood? So the D1 is 1 and D2 is also 1. So this is 0 and this is also 0. So as I have told you, when D2 is equal to 1 and when D3 is equal to 0 and D2 is equal to 1, irrespective, so don't care about this D1 and D0 because that is the priority encoder concept. So when D2 is equal to 1, you will get the output 1, 0 like this. When D3 is equal to 0 and D2 is equal to 1, irrespective of remaining inputs, the output is going to be 1, 0. Okay. Now see for the third one, last one. So the maximum value here is VR. So you are applying VR here, you are applying VR here, and you are applying VR here. So in all the three cases, what you have is V plus is greater than V minus. So in all the three cases it is going to be 1, 1. So all the three inputs are 1. So this is anyhow grounded, it is 0. So when D3 is equal to 0, irrespective of other inputs, because D3 has the highest priority, its corresponding output will be obtained. So it is equal to 1, 1. Okay, so this is how we will get all the four possible digital values of this 2-bit input, 2-bit output. Okay, so it all now depends on the value of VA. Okay, so it all now depends on value of VA. So if VA value is between this. So it depends on VR. So if VR value is in this range, you'll get the output as 0, 1. Okay, so if V in values or VA analog input voltage is in this range, in this particular range, they will get the output as 0, 1. If the analog input value is in this range, then you will get the output 1, 0. If the analog voltage range is in this range, okay, so you'll get the output as 1, 1, right? So if it all depends on the range of V in which you are applying. So range of V in which you are applying, you will get the corresponding digital outputs. So this is how the analog input or analog input voltage is converted into digital output voltage. Okay, so this is about 2-bit flash ADC. Let me take one more slide. I'll explain you about 3-bit flash ADC. Okay, because in the exam, if you are asked to write for theory exams, you have to write about 3-bit flash ADC only. Okay, so once you understand 2-bit flash ADC, so we are now seeing 3-bit flash ADC, just an extension concept. Okay, so 3-bit flash ADC, we are taken here the priority encoder of highest order. Okay, so 8:3 priority encoder. Okay, so 8:3 priority encoder, where you have 8 inputs here. So D7 has the highest priority and D0 will have the lowest priority. Okay, so its corresponding in outputs will be 3 in number. So A, B and C have represented it with this. So here we are using 7 comparators, 1, 2, 3, 4, 5, 6 and 7, totally 7 comparators. So once you understand the concept of 2-bit comparator, 2-bit flash ADC, then this is very easy. So the voltages here, how can you find the first voltage? Vx is equal to the supply voltage is VR. Now we are finding the voltage across this only resistance, which is R. Okay, so into R divided by totally 8 resistances are there. So RR gets cancelled, so we'll get VR by 8. So this voltage here is VR by 8. That means that is applied across the first comparator. Okay, sorry, 7th comparator of course. So the voltage here will be 2 VR by 8. Voltage here will be 3 VR by 8. Here 4 VR by 8. And here it will be 5 VR by 8. Here 6 VR by 8. And here it will be 7 VR by 8. Okay, so the voltage here is applied, which is equal to 7 VR by 8. So correspondingly I have taken all the ranges. So 0 to VR by 8, VR by 8 to 2 VR by 8, 2 VR by 8 to 3 VR by 8, as we have seen. Same in the case of 2-bit flash ADC. There you have got 4 cases. Now we'll get 8 cases because it is 3-bit. Okay, so all the ranges I have taken, right? So for all the ranges, so for the first one, because the input voltage maximum value is VR by 8, so this is also VR by 8. Okay, so this is V in is also VR by 8. So output of all comparators is going to be 0. So output of all comparators is 0. So the output is 0, 0, 0. Since for the second range 2 VR by 8, output of first comparator is going to be 1 and remaining all comparators are going to be 0. Okay, similar to the case which we have seen in the 2-bit flash ADC. Okay, so and the corresponding output is 0, 0, 1. Similarly, when the highest value is 3 VR by 8, output of first 2 comparators 1 and 2 both will be 1. Okay, so this output will be 1 and this output will also be 1 because the input here applied is 3 VR by 8 and the inputs here is 2 VR by 8 and here input is VR by 8 only. So always V plus is greater than V minus. Therefore, the outputs will be 1 and 1. Okay, so the corresponding output will be 0, 1, 0. And similarly, if you extend the concept, you'll get like this. Okay, so this is the concept of 3-bit flash ADC. So for n-bit flash ADC, so number of resistors, 2 important points. Number of resistors required is equal to 2 power n. Okay, so here if you see for 3-bit flash ADC we have 8 resistors of our value, so it will be 2 power 3, which is equal to 8, right? Second point here is number of comparators. This is asked most times. Okay, number of comparators required in n-bit flash ADC is 2 power n minus 1. Okay, so for 3-bit flash ADC we require 7 comparators, which is 2 power 3 minus 1, 8 minus 1, which is equal to 7. So remember these 2 points, very important. But number of resistors required is 2 power n and number of comparators required is 2 power n minus 1. Okay, so the important points I'll write once again here. So the total number of comparators required in n-bit flash ADC is equal to 2 power n minus 1. Number of resistors required in n-bit flash ADC is equal to 2 power n. So in the previous case we have seen 8, and for 2-bit flash ADC we have taken 4 resistors. So generally n-bit requires 2 power n resistors. Third, which is very important, maximum conversion time required for flash type ADC is equal to 1 into T clock. That is, only 1 clock cycle is required, because depending on the value of V in one of the ranges. So I have told you 8 ranges for 3-bit flash ADC. Yes or no? 3-bit flash ADC, I have given you 8 ranges. So in those 8 ranges, one of those 8 ranges only this V in will exist. So this V in will exist in one of those ranges, because the maximum value of V in is VR. Okay, so maximum value of V in allowed is going to be VR, reference voltage. So V in will lies in those one of those 8 ranges, and based on that 8 ranges, one of the 8 ranges, you will get the corresponding digital output. Okay, so you are getting one corresponding digital output. So it does not depend. So fourth important point is flash type ADC does not depend on input magnitude. Okay, so for any value of V in, it takes only this amount of time. So it is equal to T clock, or 1 into T clock. So it takes only 1 clock cycle in order to complete the conversion, or from analog to digital. Okay, so from analog to digital conversion, it will take only 1 clock cycle. Okay, so that these are the 4 important points which you have to remember for all the competitive exams. Okay, and remember the operation also of flash type ADC, both 2-bit flash type ADC and 3-bit flash type ADC. Okay, so now we'll see a gate problem, previous gate problem. So then a very simple problem. These type only will be asked, or otherwise they will ask you on this. Okay, so number of comparators, number of resistors, and maximum conversion time. These are the only 3 possible ways to ask in many competitive exams, except some standard exams like GATE. Okay, so the number of comparisons carried out in 4-bit flash type ADC is, so we know that number of comparisons means number of comparators. So number of comparators, I have given you the formula, which is 2 power n minus 1. So 4-bit flash ADC means n is equal to 4. So 2 power 4 minus 1, which is equal to 15. So 15 is your answer. Okay, so this is about flash type ADC and its important points. Okay.